Hi everyone, let's look at a few examples of how to work with the second fundamental theorem of calculus. Remember that the second fundamental theorem of calculus is the one that confirms that inverse operation relationship between integration and differentiation. And what you'll notice with every second fundamental theorem of calculus problem is that they are all set up the same way. You're always taking a derivative of an integral. So if you look at this one here, we are asked to evaluate the derivative, d dx, of the integral from 0 to x of the square root of t squared plus 1 dt. If you think back to the short lesson you had on the second fundamental theorem of calculus, remember what we're going to do is substitute the upper limit of integration, which is x, into the variable in the integrand. Remember that it is required that the lower limit of integration be a number. As we do that, we obtain for our answer square root of x squared plus 1, and that's our answer. That's it. Notice how we no longer have the derivative notation. We no longer have our dt differential. And the reason for that goes back to the little algebraic proof we did of why this shortcut works. Let's take a look at another example. In this one, we are taking the derivative of the integral from x to 3 of square root of 1 plus t to the fourth dt. Remember that requirement, though, that the lower limit of integration be numerical. And that's where we have a problem with this first. So what we need to do is rewrite this so that the lower limit of integration is the 3. And the way in which we do that is by negating the entire problem. This is one of those properties of integrals that you studied back in the first lesson. In negating the entire problem, we are able to switch the limits of integration, but keep the remainder of the problem the same. Now we can go ahead and complete the problem as we know to do. We are going to substitute the upper limit of integration x in place of t in our integrand, and we obtain for our answer the opposite of the square root of 1 plus x to the fourth. Don't forget that negative out in the front that we needed to reverse the limits of integration. We have two more examples to look at. In these next two examples, you'll notice that our upper limits of integration are no longer simply x, they are some function of x. Here we have the derivative of the integral from pi over 2 to x cubed cosine t dt. As we have learned to do, we are still going to take this upper limit of integration. Notice the lower limit is numerical and the variable is in the upper limit of integration. We're going to take x cubed and substitute that in place of t in our integrand. When we do that, we have cosine of x cubed. Now what we need to do with this, though, is multiply by the derivative of that upper limit of integration, which of course the derivative of x cubed is 3x squared. And that becomes our answer. We can leave it like that. If you care to rewrite it, we can put the 3x squared in the front. Notice as we do this process, we lose the derivative notation in the front as well as the differential. The proof as to why this works is very much related to that algebraic proof we saw in the lesson video. Let's look at one more example similar to this one. Here we have the derivative of the integral from 0 to x squared of 1 over the square root of t squared plus 1 dt. Once again, we're going to begin by taking the upper limit of integration, which is x squared. We're going to substitute that in place of our t in the integrand. We then have 1 over square root of x squared squared, which we'll simplify that in just a second, plus 1. But remember, now we need to multiply by the derivative of that upper limit of integration. And that derivative would be 2x. Our answer in the end then is 2x over square root of x to the fourth plus 1. Where you'll see these typically are on the multiple choice part of the AP exam, and they often are similar problems to these. You just need to know how to do them and how to spot them when you come across them. That's usually where people get stuck, is they just don't recognize it when they come across it.